How can we determine the hybridization of an atom? Fortunately, you don't have to memorize every molecule individually. Chemists use a simple quantity called the steric number. Once you know the steric number, determining the hybridization becomes quick and easy. So how do we calculate the steric number? We use a simple formula. Steric number equals 1/2 multiplied by V plus M minus C plus A. Now let's understand what each letter represents. V is the number of valence electrons in the central atom. M is the number of monovalent atoms attached to the central atom. Monovalent atoms are atoms that usually form only one bond, such as hydrogen, fluorine, chlorine, bromine, and iodine. C represents the positive charge, or the charge on a cation. If there is no positive charge, simply use 0. A represents the negative charge, or the charge on an anion. If there is no negative charge, again, use 0. Now let's apply this formula. Take methane, CH4. The central atom is carbon. Carbon has 4 valence electrons, so V equals 4. There are 4 hydrogen atoms attached to carbon. Hydrogen is a monovalent atom, so M equals 4. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 4 plus 4 minus 0 plus 0. That equals 1/2 of 8, which is 4. So the steric number of methane is 4. A steric number of 4 means the hybridization is sp3. And, as we learned earlier, sp3 hybridization gives a tetrahedral geometry with a bond angle of approximately 109.5 degrees. Now let's solve a few more molecules. You'll notice that the process is exactly the same every time. Carbon dioxide, SO₄. The central atom is carbon. Carbon has 4 valence electrons, so V equals 4. There are no monovalent atoms attached to carbon. Oxygen is not a monovalent atom. Oxygen is a divalent atom because it usually forms 2 bonds. So M equals 0. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 4 plus 0 minus 0 plus 0. That equals 2. So the steric number is 2. A steric number of 2 means the hybridization is sp. As we learned earlier, sp hybridization gives a linear geometry with a bond angle of 180 degrees. Now let's look at the ammonium ion. NH4+. The central atom is nitrogen. Nitrogen has 5 valence electrons, so V equals 5. There are 4 hydrogen atoms attached. Hydrogen is a monovalent atom, so M equals 4. The ion has a positive 1 charge, so C equals 1. There is no negative charge, so A equals 0. Now, substitute the values. Steric number equals 1/2 multiplied by 5 plus 4 minus 1 plus 0. That equals 4. So the steric number is 4. A steric number of 4 means the hybridization is sp3. Its shape is tetrahedral, with a bond angle of approximately 109.5 degrees. Now let's solve phosphorus pentachloride, PCl₅. The central atom is phosphorus. Phosphorus has 5 valence electrons, so V equals 5. There are 5 chlorine atoms attached. Chlorine is a monovalent atom, so M equals 5. There is no positive charge, so C equals 0. There is no negative charge, so A equals 0. Now substitute the values. Steric number equals 1/2 multiplied by 5 plus 5 minus 0 plus 0. That equals 5. So the steric number is 5. A steric number of 5 means the hybridization is sp3d. Its shape is trigonal bipyramidal, with bond angles of 90 degrees, 120 degrees, and 180 degrees. Finally, let's solve the sulfate ion, SO₄². The central atom is sulfur. Sulfur has 6 valence electrons, so V equals 6. There are no monovalent atoms attached. Oxygen is not a monovalent atom. Oxygen is a divalent atom because it usually forms two bonds. So, M equals 0. There is no positive charge, so C equals 0. The ion has a -2 charge, so A equals 2. Now substitute the values. Steric number equals 1/2 multiplied by 6 plus 0 minus 0 plus 2. That equals 4. So the steric number is 4. A steric number of 4 means the hybridization is sp3. Its shape is tetrahedral, with a bond angle of approximately 109.5 degrees. Notice something interesting. No matter how different these molecules look, the process never changes. Simply calculate the steric number, identify the hybridization, and from there you can immediately predict the molecular geometry and the ideal bond angle. That's the real power of the steric number method.